Welcome, everyone, to today's seminar about modern software engineering. My name is Alexander, and I will be your host today, where we will talk about the transformation to continuous delivery. First of all, can we just check if the audio quality is okay? Can everyone hear? No comments in the chat. Yes, perfect. So if you have any questions, please ask them in the questions and answers form in Zoom, and we'll try to answer your questions best we can at the end of the seminar. All right, let's get started. We're approaching, we are approaching the fourth industrial revolution, or rather we're in the middle of it. Whereas the first industrial revolution was the steam machine and mechanization, and then we moved on to series production, assembly lines, electricity, which revolutionized our ways of working and our societies. We came to automation through electronics and computers, and then we had the internet, which changed our lives. And now we have more advanced technologies consisting of Internet of Things, big data, machine learning, and artificial intelligence. And these technologies are changing our lives as we see them and changing our civilization, for that matter of fact. This technology leap consists mainly of software products, and software tools. So software is something that we use to solve problems. We go from some form of problem to a working solution. And the path in the middle, that's the question. How is it made? Because to most people, this is just something that happens, especially those who don't work in the software industry. But the thing is, most companies that have software or are software companies, they don't always understand the very basics of this either. So it's a matter of management saying the devs will figure it out sometimes. And that's what we try to dispel today, how to work with modern methods for creating working software. Why is this important? Because if you don't understand the mechanics of the engine that drives your business, it's pretty risky business. It's just luck or magic that software somehow makes your business succeed if you don't understand how it works. And let's face it, software development today looks basically like this. It's basically an assembly line process where we have product development or software development or any kind of development. And it's basically coming from the waterfall. We all know this structure. And some people tend to move it into a more circular form. And if you decide to change it into a donut, it's still basically waterfall. But what if I told you that there is a better way? A way that you can have cheaper, faster, and better software, or you can at least deliver it faster. Because this is actually where we're heading in the state of the art of software development nowadays. But this might seem counterintuitive. Why should you mass produce software? Why is that a good idea? Well, first of all, let's look at some of the companies that have succeeded. Take Flickr. They have 20 deploys per day. This is old figures, by the way, but Netflix, they did 5,000 modifications to production code every single day. That wouldn't be possible if they didn't work according to certain standards to mass produce software. What mass production of software does is that it enables automation. You can automated steps throughout the chain. Documentation, code generation, testing, building, integration, configuration, deployment. All of this can be automated, basically. And especially with AI, more and more things become easier to automate. So we are looking at a future where we can start having everything as code. And sometimes, or in a very near future, we can even start to look at it as prompts in certain cases. What this does, what this mindset enables us to do, is to have a sort of zero-touch policy where you can go from an idea to deployed software without any necessary human interaction except for the early parts, the requirements phase and the coding phase. The rest, from check-in to commit all the way to production, is automated. Why is this good? What are the benefits of this? First of all, it's cost reduction. You take less time and you eliminate risk. So with lower costs of operating, you can produce higher output and you reduce the errors and you increase the security because you have very sophisticated quality assurance mechanisms in place. And the key to this is your software factory, because we can basically look at software development as a factory. And that's the tool. In conventional thinking, you would have a factory and one laborer produces one unit of output. And if you increase the amount of laborers, you increase the amount of output linearly. What automation enables us to do is, by investing in the factory, you can increase the output per laborer without having more laborers, basically. And by increasing the investment in the factory, you can further increase the output per laborer. This is what it's all about. This is what automation enables us to do. So let's look at some of the core principles behind this. Which are the core principles? First of all, let's take a step back and look at what an ideal software development process would look like. What do we want from that type of process? We want something that minimizes our work. We want it to enable us to put attention to quality early and produce quality output as well. We want something that optimizes collaboration. We want to be able to change rapidly. If the market changes or the needs of the users change, we want to be able to reflect that quickly. We want to be able to regularly verify the progress that is made. And we also want to be able to deliver incrementally in small steps, because smaller steps are easier to control. It's easier to change smaller changes. It's easier to check smaller changes, and it's easier to handle or manage smaller changes. And in the end, we want this process to deliver functional, usable, and robust systems. So going back to this step from problem all the way to a working solution, we need to figure out what happens in the between. And the something part consists mainly of understanding the problem, then solving the problem in whatever way we find practical, and then confirming that the solution works. In software development, this most of the time translates to having requirements, code, and tests. This is the gist of it. So this is the very basics of our software development process. But there's a lot more that we can say about how we want an ideal process to enable all of those goals that we mentioned earlier. If we look at the early parts, we want to be able to go from idea to some form of requirement. These are basically user stories in most companies, or some kind of description of user needs. These break down the idea to more details, but it's important that we don't focus on how this solution works right now. We just want to break down the problem that we want to solve into smaller pieces. What are the actual needs, and what are the things that we need to do to solve the problem? Then we further move on to specifying these stories as examples or the specified behavior. This can be acceptance criteria, for example. And then this models how we want the software to behave and the system to work, basically. You still don't describe how it's supposed to solve the problem. It's just what the expected outcome is for each step, or each interaction, rather. What we can then do is to translate this into some form of executable specification where we can have this run automatically. This is done through multiple different ways of working. Behavior-driven development, or acceptance test-driven development, or specification by example, or there are many ways to do this. Gherkin syntax, where you can take acceptance criteria and then translate them into executable code. But this allows us to automate a lot of other things. This becomes our documentation. And the changes that we make to the system, we won't break the specification unless the needs actually change. So all of this chain will still be valid regardless of what changes we make to the software, unless the user needs change. So this is the way that we ensure that we have solved the actual problem that we try to fix. This is one of the ways that we talk about shift left. This is one of the implementations of shift left, rather, that we can move the focus to quality earlier in the chain. So instead of being out here talking about quality assurance and doing all of the typical testing activities, we can start with assuring or managing the quality, rather, earlier in the project, way over here. And a lot of these different puzzle pieces put this picture together. And then we come to the continuous ways of working: continuous integration, continuous delivery, continuous deployment, etc. So these are ways of working, or these are mindset or cultures that actually enable us to work in a specific manner that is very automation friendly. But let's talk about what the differences between these are. If we talk about continuous integration, we're basically just saying that all the changes that we made to the code is merged to the main branch often, and then we test these changes automatically. It might be with unit tests, or it might be with some other form of test, integration tests to our system. And this fictional pipeline or build chain looks very different from place to place. So don't take this as some form of granted model. It's just an explanation for this. If we talk about continuous delivery, it's when we automate all the steps after the continuous integration, all the way until we are able to deploy to production. But the deployment step is made manually. So we basically have always deployable code, or at least if it passes all of our QA checks along the way. Taking this step even further, we automate the deploy step as well into production. So what we have here is that every commit that is made by a developer, all the way over here, every change that is made to the code will automatically go all the way into production if it passes all of the quality assurance steps along the way. This is a fully automated build chain. And we can build stuff at the end of this as well, like monitoring and automatic rollbacks and things like that, but that comes later. But when this works well, together with the executable specifications, this creates a system where you have full traceability from the requirements, all the changes that are made, all the way out to software in production. And this is something that is extremely valuable when you work in a regulated industry, where you need full traceability. But the deployment is not all of it. We also need to talk about life cycles, architecture, packaging, commissioning, and infrastructure. And this can be done in multiple different ways. There are so many ways to combine these. And you have some companies where you maybe have agile ways of working, you work with N-layer architectures, but you still run it on physical servers or on your premises. Then you might have some other place where you have continuous integration, N-layer architecture, virtual servers, but you deploy onto the cloud. Or you use microservices and containers and run it on a data center. There's no right or wrong way, but the lower down in the chain you are, the easier it is to manage and scale this entire automated way of working. And especially when it comes to doing lots of small changes with microservices and containers and the cloud, where you can scale up and down depending on your needs, that makes it a lot easier to automate fully. And if you take automation all the way to the extreme, you can end up with something called no ops, where you don't need an ops team that actually does operations for you. This is handled by the development team themselves. Technologies that are important for this is using like infrastructure as code or some form of PaaS platforms or serverless architectures, for example. And this is especially more applicable in the cloud native environments rather than the more classical environments. So if we look at the difference between these, most companies have dev teams and they have ops teams. And the dev teams basically gather requirements, they code and they test, and then they deliver this to the ops team. And the ops team takes over, they distribute and maintain the product from that point over. And this is basically a handshake, and then the ops dev team lets go of the product. More and more companies are moving to DevOps, where you have a way of working or a mindset that fosters collaboration between these two different teams. And you can leverage the automation to streamline the entire software development lifecycle. And these teams both often have both development competencies and operations competencies. You may have specific team members that do either or, but both the competences are there in the team. Moving further and talking about no ops, this is basically a concept where the IT environment is so automated that there is no specific need for ops teams. You have an underlying infrastructure that can handle all the way from commit to deploy. So this can be automated fully. There's not many companies that can do this, and this is basically depending on what type of industry you're running in as well. This might not be feasible for everyone. It's not supposed to, but there are cases where this is extremely valuable. So if we look at this chart again, where we have the different ways of working and the different infrastructures, etc., we still see that the further up we are in this chart, this is the more old school ways of working, and this is sometimes necessary. Well, we don't need to work linearly across these lanes. We can combine different aspects of these lanes, depending on what type of software you're developing and what type of services you have. But what this does is that it allows something called progressive deliveries. You can have incremental rollouts of your software. And this is different from continuous delivery because you always put into production what the latest software is or the latest version, but you don't always enable these features for everyone. You can enable them for some users or a subset of users. So what this does is to enable A/B testing if you want to beta test features, or if you have specific times where certain features should be enabled, if you run campaigns or something like that. And also things like nice to have features like panic buttons. Oh, something went wrong. Push the panic button and automatically roll back to the previous version without actually having to deploy new software into the systems. You just disable the new features. Or something like premium features, which only a subset of users should have, is also easy to manage with this kind of feature flagging. So just because we put something into production, it doesn't actually need to be the way that everyone gets access to it. You can have code in production that no one has access to, features in production environments where no one can access them. You control this. So there are ways to secure that whatever you put into production can be useful, but also does not always have to break the system. If you're uncertain of the quality, of course, but you should always work to secure the quality before that step is taken. So basically, we have a way to run A/B tests or beta tests, dog fooding, canarying even if you roll out a new version and you start gradually increasing the user base that is running on the new version to see, will it work? How's the performance? And all different types of pros and cons that you get from having progressive deliveries. This also produces some next level challenges in the quality assurance. So you might be familiar with the complicated versus complex problems, where complicated problems are something that consists of many components and dependencies, but they can be described and modeled. You can predict a cause and effect with them. So you don't have to do the guesswork. You can basically model the entire behavior and then try to figure out all of the edge cases or test whatever can happen. It's possible to do exhaustive testing, but it's not maybe always the right thing to do. It's not always feasible, but it's possible. Whereas in the complex domain, you have so many components and complex dependencies between these that it's difficult or impossible to describe this system in its entirety. And it's extremely difficult to predict cause and effect in these kinds of systems. And this can be like traffic systems or any other type of complex software systems where you have too many factors that can weigh in to the behavior and the outcomes, that it's difficult, especially when they have large user bases using the same type of features or the same system at the same time. So what this kind of system does is that it increases the risk a lot. But you want to minimize the risk. So what do? Because the cost of 1 hour of downtime for basically 98% of all organizations exceed $100,000. In Gartner, they made a survey in 2014 where they found that basically the average cost of 1 hour's downtime is $300,000. Apple had a 12-hour outage in their store, costing the company $25 million in 2015. A 5-hour power outage in an operations center for Delta Airlines, they canceled 2,000 flights, and that cost them an estimated of $150 million for a 5-hour power outage in 2016. In 2019, a 14-hour outage cost Facebook an estimate of $90 million. So 1 hour of downtime can be extremely expensive. How do we minimize the risk for these kind of occurrences? Well, we can take some inspiration from the Nobel Prize laureates of 2019 economics. They were awarded for something called randomized controlled trials. So basically, you take a system which is in production and you randomly run controlled trials on them. It's like having someone pulling a wire here or there, or shutting down a service and seeing what happens in a controlled environment. You can do this in production, or you can do this in staging environments. But when you do it, you can quickly roll back if something goes completely wrong, and you are in control of this. Because whenever you have some form of outage and you do the analysis of what went wrong post-mortem, that can be pretty good, right? To understand what went wrong and why did it go wrong and how can we avoid that happening again. But it's even better if you do it pre-mortem, that you can actually predict these kind of things and try them out in a controlled environment and see what happens. This is referred to as chaos engineering. That's the term for trying out what happens. Let's just do this and see what happens to the environment and to the software. And then we can learn from those mistakes before they occur. So basically, if we put all of this together, we have automation as top priority. If we understand the 6 C's of the DevOps cycle, and we make sure to apply automation between these steps, that is the key. And with this, we can also put the continuous quality assurance steps that we take with automated tests and exploratory tests where they are applicable, and maximize the quality all the way from idea all the way out to operations, where we have all the steps in between with maximum collaboration, brainstorming, and automation used for the right things. Because automation is supposed to eliminate repetitive tasks. We're not supposed to automate away those things that actually bring value from our co-workers or laborers or whatever we want to, what type of system we are developing a process for. We want automation to make things easier and safer and faster. That's what it's supposed to do. But it doesn't take away the ingenuity or the creativity. Using that as a guideline, that's when you really, really get value from automation. Thank you all. That's the end of the presentation. If you have any questions, feel free to ask them in the chat and we'll answer these the best we can. Jilan has a question about software automation. Could you write the question? I don't know if we can unmute you. What challenges do you think there will be in automating the requirements? Well, of course, this is a very good question because we don't always want to automate the generation of requirements because it's still people who need to understand the needs of the users. So we need to understand what our users actually do, what are the pains and gains, and what are the problems that they face. And then when it comes to solving the problem, that's when we can use, for example, AI to leverage that as a creative tool to both create good specifications, which of course should be reviewed by people, but also to create the volume of documentation that can help the quality be where it should be. You don't always want to do too much documentation because it can be a waste of work in some cases, especially when you have a very changing user need scenario or where the problem domain is very complex and you need to adapt quickly and change your features or your system to adopt new ways of working or new market tendencies, etc. So using AI as a leveraging tool to put more or less effort and gaining more output, that's one way to do it. And also incorporate these into LLMs for future prompting and AI automation of tools. Yes, exactly. So you can use whatever you have to also train LLMs to generate more of the same type of understanding, and then you can innovate on that or create more out of that. Welcome. How would you approach implementing this type of approach in an old organization with a lot of legacy systems, code, and departments with different grades of maturity and understanding this type of approach? That's a very good question. And this is, of course, a big challenge for many companies. I think there's no easy answer to this without understanding more about the product. But one thing that I have done with my clients that I've worked with is to take on a step-by-step approach where we find what is the feasible level of automation that they can have, and then work backwards towards where they are now and try to build a roadmap. Where do we want automation? Where can we not expect to have automation? And where will it actually benefit the organization? And then step by step implement, starting from the new code that is written, or whenever you do maintenance. Then, for example, say that you don't have any unit test cases for your entire code base. You can then introduce a rule that every time you make changes to the code, you should write unit tests for that specific piece of code. So over time, you will gradually build up a larger volume of unit test cases, and then also start to look at where can we gain benefit from automation in even this old pipeline. I mean, build pipelines can most of the time be automated, but it's just a matter of effort and what are the gains from that. And how do you quality assure between the different stages in the software rollout phase? So running automated integration and then deploying this to a test environment and automatically running tests, that might be a very feasible stage. But then when you come to the acceptance testing phase, there might not be any good tool or good way to automate the acceptance testing. That might have to be done manually. Or you actually have a very strong need for exploratory testing. That's where you can use that without compromising on the human part, because exploratory testing is not done so well by AI or any other type of automation. So you want to automate where you can get benefit from that, where you have high repetitivity, but don't automate the parts where you have low repetitivity or you have a lot of high level of novelty in the product, for example. But starting small and then increasing step by step, that's the way to go when you already are facing a lot of legacy code and old types of systems. And then maybe you can gradually move to more modern architectures or move it to a different type of hosting environment, for example, gradually. You can pick out parts of the software that are not business critical and sometimes move them out into another type of service. And then, of course, this will build a high complexity in the system. But if it's a type of system where you cannot just tear it apart and start over from scratch, which most business critical systems are, you need to find a way to gradually move from one type of system to another. So it's very system dependent and very company dependent, but small steps incrementally, I would say, is the key there. All right, everyone. Thank you all for your attention. And this will be recorded and we will put it on YouTube. So find us there. And if you have any questions or you want to bounce some ideas, feel free to connect with me on LinkedIn. Thank you all. Have a great week.